Good morning to all of you. In previous session, we have seen basic building blocks that can be used for the realization of discrete time system, right? So we have seen an adder, a constant multiplier, signal multiplier, unit delay element, unit advance element. So these five basic building blocks can be used to realize discrete time system. So in today's session, we'll be discussing an example of discrete time system, how it can be represented using these building blocks, right? So let's begin today's session. So here example is specified. So using building blocks, basic building blocks, you have to sketch the block diagram representation of the discrete time system, okay, which is described by input output relation. Y of n is equals to 1 by 4 y of n minus 1 1 by 2 x of n plus 1 by 2 x of n minus 1. So where this x of n and y of n, x of n is the input and y of n is the output, okay. So let's try to identify the realization or block diagram representation of the given discrete time system, right? So here in solution I am rewriting the given input output equation, right? The given input output equation is that y of n is equals to, is the equation 1 by 4 y of n minus 1 plus 1 by 2 x of n, right? It is given here, right? 1 by 2 x of n plus 1 by 2 x of n minus 1, okay. So if you observe, whenever we are representing these input output equation, but whenever I am considering any system, okay, so this output y of n is produced by the system, okay. Y of n is produced by the system capital T when you are applied the input x of n, okay, because there is only one input x of n in this case, okay. But when it produce an output y of n, right, then how it has been, this output is produced here. So the input is multiplied with 1 by 2. Similarly the inputs delayed version has been taken, and again it is multiplied by 1 by 2, it is added into that quantity, and again the previous output y of n has been taken, which is multiplied with 1 by 4, okay. So if you observe this input output relationship, then the output y of n comprises three terms, right? So these last two terms are the input terms, right, while the first term is nothing but the output, okay. So that means if you want to identify the output of the system, then this output y of n depends on current input x of n, past input x of n minus 1, as well as past output or previous output y of n minus 1, right? So let's try to represent this discrete time system using block diagram representation, right? So initially we will realize the input part, right? So here we will be applying input x of n. So if you observe the input, so input is getting multiplied with 1 by 2, that is nothing but 0.5, okay. 1 by 2 is nothing but 0.5, right? Similarly the second term, in second term it is delayed by one time unit, and again it is multiplied with 0.5, right? So here I can draw this block as, here if I am trying to realize this last term, so initially input is delayed, right? Input is delayed, so I will use an delay element, unit delay element, okay. I'll use an unit delay element here. So the output of this unit delay element will be what input you have applied here, x of n, so output will be x of n minus 1. then I have to multiply that x of n minus 1 with a constant which is nothing but 0.5, right? Similarly, this x of n is simply multiplied here with a constant 0.5, right? So I have used one unit delay element and two constant multipliers here, right? So here this x of n is coming as it is, right? And it is getting multiplied with zero point 0.5. So the output will be 0.5 multiplied by x of n, that is nothing but 1 by 2 x of n. And here it is getting delayed by one time unit, so output is x of n minus 1. Here output is x of n minus 1, then it is getting multiplied with 0.5, so that means 1 by 2 multiplied by x of n minus 1. Next I have to add these two values. Okay, so I have to add these two values, so I will require an adder, right? So I'll be adding these two values by using an adder, right? So after adding these values, next I have to add this remaining term, okay, into this resulting value. I have to add this remaining term, right? So how it can be done? So again I will be requiring, or I need one adder, okay, to add this. But if you observe here, right, this term here is y of n minus 1. It is not an input term, okay, so it is derived from the output itself, okay, so it is nothing but the past output or the previous output, right? So if your output is y of n here, okay, so that means I have to take this output y of n, okay, and I have to feed back this output to the system, okay. So this output will be feedback by taking its delayed version, okay. So here this output is coming, right? So it will get delayed by one time unit, so y of n minus 1 will be the resulting output here, right? Then I will be multiplying it with 1 by 4, okay. So I can write it as 1 by 4, I can write it as 0.25, okay. So I have used here one delay element and one constant multiplier, right? So here the output is y of n minus 1, right? So it is getting multiplied with 0.25, and then I will add this term, that is 0.25 multiplied by y of n minus 1 in the previous term, okay. So that previous term was 1 by 2 x of n plus 1 by 2 x of n minus 1. So here the resulting addition, and finally this output y of n will be produced. So this is nothing but what you can say the block diagram representation of the given discrete time system, right? So we'll be revisiting this topic, okay, in your fifth and sixth unit, where we'll be looking the realization of or block diagram representation of FIR and IR system, that is finite impulse response system, infinite impulse response system, as well as some filters, right? So we'll be again using these basic building blocks for the realization, but there we are using cascade realization, parallel realization, right? Lattice ladder structure realization, frequency sampling realization. So all those realization will be looking in fifth and sixth unit, right? But here we are used how many basic building blocks? So two daily elements, right? Two adders and three constant multipliers, right? So this figure represent what? Block diagram representation of given discrete time system. Discrete time system, correct? So again, I can modify this given input output equation, and that is the solution, okay. Or I can modify this input outputs equation as y of n is equals to 1 by 4 y of n minus 1, right, plus Here I can take 1 by 2 common, right? So in bracket I will write x of n plus x of n minus 1. Okay, so if I want to realize the discrete time system by using this equation now, right? So again input is x of n, and here again if you observe, this x of n is directly added here, right? It has been added here. So this x of n is directly coming as it is, right? Here it is added with the delayed version of x of n, that is x of n minus 1. So I will take one delay element z inverse, right? And I will add it with x of n. So here input is x of n minus 1 and here it is x of n. Okay, so here the addition of x of n plus x of n minus 1 is there, right? But I have to multiply the resulting addition with 1 by 2, constant 1 by 2. So I'll be using constant multiply here now, right? So I will use this constant multiplier. I can specify it as 1 by 2 or I can specify it as 0.5. Okay, so I am multiplying it with constant 1 by 2. So I have used one adder, one delay element and one constant multiplier. Previously I was using two constant multiplier, but now I reduce the element. Okay, instead of using two constant multiplier, I am using here single constant multiplier. Again on output side, again I had to feed back this output into the system, okay, to get its what the delayed version, that is previous output. So I will use here z inverse, right? So it is producing the output y of n minus 1. So this y of n minus 1 will be getting multiplied with the constant, that is nothing but 1 by 4. So this is nothing but your 1 by 4 multiplied by y of n minus 1, then it will get added with the remaining terms. Okay, so here the at this point the input to this adder is 1 by 4 y of n minus 1, right? And it is getting added with the, here what is the input? So in this case it is 1 by 2 x of n plus x of n minus 1. Okay, so this is another realization of this same input output equation, but the difference between these two realization is, here I was using, in previous realization I was using three constant multipliers. Okay, here I am using only two constant multipliers. Okay, so one element has been reduced. So obviously when you are reducing the number of elements, so obviously the cost of realization will get reduced, right? So that is all about what, obtaining discrete block diagram representation of the given discrete time system using its input output equation, right? So in next session we'll be looking the classification of discrete time systems. Okay, so we'll see the generalized classification of the discrete time systems, as well as we'll be looking some examples, okay, when we'll go through the classification of discrete time system. So thank you for joining this session.